Hello, welcome to part 2 of week 8 of the ECE 9013 course. In this part, we will be discussing the concept of orders of growth and provide an overview of the different complexity classes. So, for orders of growth, the goal is to evaluate the program's efficiency when the input is very large. We would like to express the growth of the program's runtime as the size of the input grows. Also, we would like to put an upper bound on the growth, which is as tight as possible. However, we do not need to be too precise, in the sense that we would like it to be described as in the order of rather than exact growth. That's why we will look at what are the largest factors in time, which means which sections of the program will take the longest to run. Therefore, generally, we want a tight upper bound on growth as a function of size of input in the worst case scenario. To do that, we use what we call the big O notation. The big O notation measures an upper bound on the asymptotic growth, and this is often called order of growth. It is used to describe the worst case, and this occurs often when a program runs. It expresses the rate of growth of a program relative to the input size, and most importantly, it evaluates the algorithm, not the machine or the implementation. So to illustrate this big O notation concept, here we are calculating the factorial of a number n. So the code goes on a while loop, and every time we multiply the value by n. So assuming that each iteration takes constant time because each operation is assumed to be one operation, the number of steps is 1 plus 5n plus 1. So in the worst case asymptotic complexity, we can describe this as in the order of n because of the fact that this is the largest factor. To do that, we typically usually ignore additive constants and we ignore multiplicative constants, which is the factor of 5 here. So what does this O of n measure, or big O measure? Since we are interested in describing how the amount of time changes or grows as the size of the problem grows. Therefore, given an expression for the number of operations needed to compute an algorithm, we would like to know the asymptotic behavior as the size of the problem gets large, in the sense that as the input size n tends to infinity. Therefore, we will focus on the term that grows most rapidly in a sum of terms. We will as mentioned earlier, we will ignore additive constants and multiplicative constants, since we want to know how rapidly the time required increases without having to know the exact value. As a simple example, here we would only want to focus on the dominant terms. So for the first expression, the most dominant term is n squared. That's why we say that this expression has an order of n squared. In this case, the same applies. As n tends to infinity, n squared is the dominant term. In this expression, the term n is the most dominant term. That's why we mentioned that this is of order n. In this case, the largest term would be n log n, because log grows faster than a constant. And in this case, it's 3 to the power n, because the exponential growth is faster than the polynomial growth. So typically, we can express orders of growth in one of several orders. We mention it's constant if the order is just a number, linear if it's in the linear combination of the size of the input, quadratic or what we can call polynomial, logarithmic, ln log, and exponential. So to be able to analyze programs and determine their complexity, we need to focus on the law of addition and the law of multiplication. So with the law of addition, which is used with sequential statements, O of f of n plus O of g of n is the same order of f of n plus g of n. So for example, if we have two consecutive for loops, one of order n and the other one is of order n squared, then we can combine them to be O of n plus n squared, which is equal to O of n squared, because n squared is the dominant term. Similarly, we use the law of multiplication when we have nested statements, such as loops. So the order of f of n multiplied by the order of g of n is the order of f of n multiplied by g of n. So here, for example, we have two for loops, each in the order of n. So O of n multiplied by O of n, because for each iteration of the larger loop, we have n iterations of the inner loop. So we get O of n multiplied by n, which is O of n squared. And this is because the outer loop goes n times and the inner loop goes n times for each outer loop iteration. So as we mentioned earlier, these provide an overview of the different complexity classes: constant running time, logarithmic running time, linear running time, log linear running time, polynomial running time, where C here is a constant, and exponential running time. So these figures illustrate how the order of growth changes based on the different classes. And this table provides us with an idea about the number of operations needed in case we have a particular input size and complexity. Thank you.